So now we're going to do some example problems from section 1.6. So to start off, we're going to find the inverse, or we're going to show that f and g are inverse algebraically, which means we're going to figure out what f of g of x is. And if it is the inverse, we should get x. That is, one takes x, does something to it, and the other undoes it, so we get x. So how do we do that? Well, we actually algebraically show this. So f of g of x would mean we take g of x, the cube root of 2x, and then we plug it into f of x, which means we cube it, and we divide by 2. Hopefully you recognize that cubing undoes the cube root, so we end up with 2x over 2, and then the 2's cancel, so we get x. So yes, that shows algebraically that they're inverses. Graphically, well, we know that x cubed over 2 is going to be some sort of cubic that has been vertically compressed, so it's going to open up a little bit wider, so maybe like that, something like that. Still going to pass through 0, 0. And the cube root of 2x is going to be very similar. So it turns out that we're going to be able to show that these are indeed reflections over the line y equals x, which is what we're trying to do when we show that they are indeed inverses. And C, numerically. Now, this is a little bit trickier. So what we need to do is we need to show that if we do f of x and then we do g of x, we get x right back, which means we need to have an x to start with. Now I'm going to do this by actually picking a value. I'm going to say 2 because I happen to know that when I plug 2 in here, I get 2 cubed, which is 8 over 2, which is 4, right? So the input is 2, the output is 4. So now if I take this input and I plug in a g of x, which means I'm going to take the cube root of 2 times 4. Well, 2 times 4 is 8. The cube root of that is 2, which means I started at x, then I ran g of x on it, and I got 4. Then I plugged that in, and I got back to where I started, which means that g of x undid f of x, which demonstrates numerically that we're looking at inverses. Same thing, different functions. So I'm going to go ahead and find f of g of x, g of x. I'm going to go ahead and redo that. F of g of x, which would mean I'm going to take g of x, which is 2x plus 3 over x minus 1, plug it in, so that means I'm going to add 3 over, well, I'm going to have that again because I have these two values of x here, 2x plus 3 over x minus 1 minus 2. Now this looks like a mess because to some degree it is, but it does mean that I have a common denominator in both cases, which is x minus 1. So I'm going to have to multiply this by, so that's 3 over 1, so it's x minus 1 over x minus 1. And this by x minus 1 over x minus 1, which means I now have some fractions over fractions. This fraction is over x minus 1, as is this one in the denominator. Now what's up top is a little bit more complicated. I have the 2x plus 3, right? Plus 3 times, I have to distribute this, plus 3x, then minus 3. Notice how to distribute. Same idea here. Still 2x plus 3 minus, so minus 2x minus negative, then negative times negative is positive 2. Simplify. 2x plus 3x is 5x, still over x minus 1. 3 minus 3 gone. 2x minus 2x gone. 3 plus 2 is 5 over x minus 1. Now remember, this is the same as taking this, 5x over x minus 1, and multiplying by the, because I'm dividing, reciprocal. Now hopefully you see that what we end up with is, well, the x minus 1's cancel, 5's cancel, so we're left with x, which demonstrates algebraically, right, A for algebraically, that they're inverses. Graph both of them. They are indeed reflections over the line y equals x. Let's try numerically. So we're going to pick a value of x, and then we're going to do f to it, and then we're going to take the value of f of x, right, and plug that into g of x. Okay, so let's pick a value. Let's pick something that ends up with a nice not too terrible a value. How about, let's see, we can't pick 1, we can't pick 2. What if we pick 3? Okay, let's try that. So let's x equals 3. 3 plus 3 is 6, over 3 minus 2 is 1, so this is 6. Which means I'm going to put 6 in here. So when I put 6 into g of x, 6 goes into g of x, right? This is kind of an important step. 6 now becomes my input, right? I'm going to get 2 times 6 plus 3 over 6 minus 1, which is 12 plus 3 is 15. 6 minus 1 is 5. 15 over 5 is 3. Did we get what I wanted? Yes. Put 3 in, got 6. Doing f of x, f to 3, means we're going to get 6. Then we take that, does this undo it? Yes, because these two match. Yay! So that shows numerically their inverses. Okay, does this function have an inverse? This can be hard to see at times, but remember, if it's an inverse, that means it's 1 to 1. If we were to graph this, it looks like the domain is hours, right? And our range is dollars, yes. Then it turns out right away we have 1/2 an hour, right? 1/2 an hour gets us $40. And we know that 1 hour also gets us $40. Now looking at that, that's still a function because it passes vertical line test, but if you were to draw a horizontal line, it fails because it's going to hit twice. So does this have an inverse? No, it does not. No inverses because it's not 1 to 1. And the problem is that these two values of the domain are mapping to the range. Now if it were invertible, then that would mean that each x would go to one and only one y, and vice versa, meaning you could have something that looked like this, and that would be, in general, what invertible would look like, just so you know. Okay, recognizing 1 to 1. This is easy. Is this 1 to 1? If it's 1 to 1, that means it's invertible. To figure out if it's invertible, we use the horizontal line test, and we discover that no, not 1 to 1, because it fails the horizontal line test. Okay, find the inverse algebraically. So what we're going to do, here's f of x, or y equals the square root of 16 minus x squared. Now they give us a restriction. Now it turns out that this is the graph of a circle with a radius of 4, so technically this is a circle with a radius of 4. If you don't believe me, try it. It does work. But what they've done is they've actually restricted the domain. So we're looking from x from -4 to 0. So we're just looking at this portion. That's what f of x actually is, right, with the restricted domain. So what does that mean? We can do our normal switch-oroo the x's and the y's, and then resolve. To undo squaring, undo the square root, we square it. Then we subtract our 16. Now please note, this negative is kind of important. When we divide by -1, it makes both of these the opposite. That's positive, that's negative. Most of the time we'll write 16 minus x squared. So when we divide by -1, it does switch that. Now someone, that's me, forgot the squareds. So this is something to look out for. Did you copy everything down from step to step? Because now we need to undo that. And are you prepared to be a little bit disappointed? Doesn't that look a lot like the original function? Well, there you go. Turns out this is indeed that. Now, it turns out its domain and its range. So we know this original function has this domain, right? Which means this has a range from -4 to 0 inclusive. What's its domain? Well, what is the range of this original function? The range of the original function seems to be from 0 to 4. Right? Which means if we're looking at this one, well, if I put in 0, that's okay. And all the way up to including 4. Remember, the domain and range flip-flop, right? And if you do look at these, well, what are we looking at? We're looking at the same thing, but reflected over the axis, which means that the inverse is just this. Hey, that makes sense then that it's the same equation. Okay, find this algebraically. So 6 over the square root of x. Not sure what that looks like, but let's take a leap of faith. So I'm going to rewrite this, switching the variables. Now, here's a technique. You ready? I'm going to multiply both sides by the square root of y, because I want to solve for it. It'd be easier if it was in the numerator, right? That means I have x times the square root of y equals 6. I'm now going to get rid of my x by dividing it, because I'm trying to resolve for y. Hey, that looks better. How do I undo square rooting? I square. Remember, if I'm squaring this, I'm squaring everything, which means that this is my inverse function, okay? And indeed, if you graph both of these, there will be reflections over the line y equals x. And here they're telling us to, well, restrict the domain of the function. So because if you look at this right now, this is a quadratic that's been shifted 4 to the right, so it's going to look like that, right? So let's be positive, right? Let's just look at this portion of the graph. So we're going to restrict the domain, so we're talking about from 4 to infinity inclusive, which means the attendant range is going to be 0 to infinity, right? 0 and up. So when I find the inverse, whatever the heck it is, f inverse of x equals ... right? I know that the domain is going to be from 0 to infinity, and the range is going to be from 4 to infinity. Why do I know this? Because remember the domain and range flip-flop. Okay, the actual process. X equals y minus 4 squared. So I switch the variables. Now I'm going to undo squaring by taking the square root. Undo subtracting 4 by adding 4, which is my inverse. So it is the square root of x. Notice how the plus 4 is outside. So it's, if you think about it, this would be, the square root of x would be this, but shifted up 4, which would be like that. So indeed would look like a reflection of the line y equals x. One more. Absolute value of, so this is all sorts of fun stuff going on. This means it's been reflected over the x-axis. 1 to the right and 2 down. Which means that if we're looking at where this is, it's going to have a vertex of 1 over and 2 down, and it's going to be reflected. So it's going to look like that. Now, that is obviously not 1 to 1. It fails a horizontal line test. So let's be positive again, and we'll look from here. So we're just going to invert that portion and ignore this. So what does that mean? Our domain is going to be from 1 on, including 1. Why not, right? Which means our range is going to be from what? Well, that point is negative 2 and down, so it's going to be from negative 2 and to negative, there you go, infinity. So when we do find the inverse, what happens? Well, the range and the domain flip-flop. So now this is negative 2 to negative infinity, and this is 1 to infinity. Now, here's where we need to think carefully. What is this function? This right here would have what? Well, this would be the same as saying that we're looking at just this portion of this graph. So we ignore this. This is just a linear equation, right? It has been shifted over 1 and then down 2, right? So what does that mean? That means that this equation is going to be negative. That is going to have a negative slope. So that portion of this graph is going to be this. What's the big difference? I took the absolute value out, right? Now it has been reflected, right? So that's going to make a difference. Is this negative x? Yes, right? So it's going down 1 and over 1. So does this work? I mean, what does this simplify to? Negative x plus 1 minus 2, which is negative x minus 1. So if you follow this, then that means it does have a y-intercept of negative 1, which makes sense. So it turns out that the piece of this graph that we're inverting is simply a linear equation. Half of a absolute value at the vertex is just a linear equation. So when I do switch the variables, don't forget the negative separate, and I take the opposite, then I'm going to get, well, remember, this negative x minus 1, they both change signs, right? That means that the inverse is just going to be, let's clean this up, is going to be negative x minus 1, and that's it. Well, let's think about that. Negative x minus 1. Well, that's going to be negative x, so it's going to have that slope of negative 1. It's going to be down 1. Hey, that's the same thing. How does that work? Well, if we reflect this over this axis, what does that do? Well, now it's talking about -2. So it's the same line, right? Except it's this way. Why? Well, the domain is from -2 and back, right? So this flips back here, and then the range is from 1 up. That's spooky. So it ends up being the same line. It's just the domain and range make all the difference in terms of the actual inverse. And that's all we've got for section 1.6 in the way of examples.